Sorry, I will start again. I'm Dave Gibson from STAR-Dundee. I'm going to talk about SpaceWire and SpaceFiber. So I'll talk about what we do at STAR-Dundee, talk about SpaceWire and SpaceFiber in general, and then finish up with some discussion on what we've been working on recently. So SpaceWire has been around for a long time now. It was standardized in 2008 with a revision in 2019. It's an ECSS standard, so it's completely open. You can go on the ECSS website and download it for free. It's been flying on hundreds of missions now, and it's still being designed into many more currently. In current FPGAs, typically runs at 200 megabits per second, or even up to 400 megabits per second now. It's bidirectional and full duplex. You can have a simple point-to-point link, or you can build an entire network with routing switches. And it has a very simple packet format. So the packet format is just an address section, a cargo, and an end of packet marker. So it makes it a very good platform to build other protocols on top of. And it has low latency timecodes for things like synchronization over the network and event signaling. So we build SpaceWire test equipment. So if you've ever used SpaceWire in your lab, or you know someone that has, you might have seen one of the little blue boxes in the bottom left there. So this is SpaceWire to USB test equipment. So you can connect from your laptop or your PC into a SpaceWire network. And we have various different form factors, so PCI Express, PXI, and so on. We also do link analysis and recording equipment. So you can place these devices along one or more SpaceWire links and then capture the traffic at very fine detail to try and debug any issues or problems that you're having, or just record massive amounts of traffic for analysis. And then we have some other specialized equipment for things like providing isolation between your expensive flight equipment and your relatively inexpensive test equipment, or proving conformance against standard, or doing deterministic device simulation, for example. So SpaceFiber, on the other hand, is the next generation of SpaceWire. So it was standardized in 2019. Again, it's an ECSS standard, so you can go onto the ECSS website and download it. And the first thing about SpaceFiber is that it's backwards compatible with SpaceWire. So it uses the same packet format, just that simple packet format. It uses the same addressing system for getting packets across the network. And you can bridge SpaceWire devices into a SpaceFiber network quite straightforwardly. But below that packet level and the network level, it improves upon SpaceWire in a few different areas. So first of all, it's much higher performance. So in typical current flight FPGAs, you can use the transceivers in the device and run a SpaceFiber link at 6.25 gigabits per second per lane, or 10 gigabits per second per lane. And more recently, we have demonstrated SpaceFiber in AMD's Versal device running at 25 gigabits per second, or 100 gigabits per second across the entire link, because it's a multi-lane protocol. So you can scale performance by just adding new lanes to the link. You can have up to 16 lanes, and if a lane fails, it will gracefully degrade down to a lower number of lanes. So if you have a quad lane link and one of the lanes fails, it just continues to operate with 3 lanes. And you can have redundant lanes to swap them in if desired. And you can have asymmetric traffic. So lanes can be unidirectional. If you have a device, for example, a camera, which has traffic heavily biased in one direction over the other, so it's receiving a small amount of control traffic, but it's pumping out massive amounts of images, then you can configure your lanes appropriately to save on mass if you don't necessarily need the traffic in one direction. So SpaceFiber, despite its name, runs over electrical or fiber optics. So with electrical, typically up to a few meters of cable, or fiber optics up to 100 meters. It has low latency broadcast messages. So these are small messages that have a channel to identify where the broadcast message is coming from. It has a type to identify what's in the broadcast message, And then it has 8 bytes of user data. So you can use this, for example, to distribute CCS, DS, time codes, or any other information. You can use it for synchronization. So recently we've used broadcast messages to trigger an instrument capturing data instead of dedicated trigger cables if you need a very low latency trigger interface to a device. You can signal events or distribute status information over the network, or do error notification, for example. And the photograph in the bottom right is a SpaceFiber routing switch that we developed during a recent project called Highside. It has 10 ports and it's 100 gigabits per second across the router. SpaceFiber also has quality of service. So if you consider a SpaceWire link, you have a single stream of data across the link, meaning that if you have 2 packets that come on, arrive at the link at the same time, one packet's going to block the other, which may be an issue. So SpaceFiber solves that by allowing multiple different streams over the same physical link by using virtual channels. And virtual channels can be assigned their quality of service. So you can prioritize certain virtual channels, you can reserve an amount of bandwidth, and you can allocate a schedule to each different virtual channel. And then you can use these virtual channels to build virtual networks. So these are independent virtual networks running on top of the same physical network according to their quality of service. So it's kind of like having multiple different SpaceWire networks running on the same physical network, independent of one another. So you can have mixed criticality traffic without having to worry about your critical traffic being blocked by lower priority traffic. Excuse me. It also has built-in fault detection, isolation, and recovery at the link level. So if you have a packet going from node A to node B across the network, and there's an error on the link, the error gets recovered from, contained within the link on which it occurred, and it doesn't propagate outside of that link, and it doesn't affect the packet's path across the network. So packets are transferred reliably from one node to the other without an end-to-end error recovery scheme. And as I mentioned before, the graceful degradation of multi-layered links means that you have built-in redundancy within your links. Also has a small footprint in FPGAs. So one of the main objectives of the SpaceFiber IP is to be very efficient in FPGAs. And I mentioned earlier that it's very straightforward to make use of existing SpaceWire equipment by just bridging it into a SpaceFiber network. And for flight heritage, SpaceFiber has been TRL 9 since 2021. It's currently flying on at least 6 operational satellites and being designed into at least 60 more. And the photograph in the background here is from Airbus's Pleiades Neo 3 satellite, which is using SpaceFiber. So we also developed SpaceFiber test equipment. For the sake of time, I won't go into too much detail, but these are PCI Express boards with SpaceFiber interfaces, or we have another flavor of the board, which is a SpaceFiber router. And the chart on the right is just a performance test showing data rate and CPU utilization over time. And it's reaching about 18 to 19 gigabits per second on, so this test was done on kind of a mid-spec PC from a few years ago, running Windows. All of our test equipment is supported by our common software suite called STAR Systems. So if you've ever used any of our devices, you might already be familiar with this. It includes a range of graphical applications to perform common functions, but it also includes a variety of different APIs, so you can control the devices from within your own software for sending and receiving packets, time codes, broadcast messages, configuring devices, building and transferring RMAP or CCS DS space packets, for example, or utilizing the triggering capabilities of the devices. So the triggering mechanism is an event-driven system, which allows you to configure and hook up different events to actions outside of the software. So you can configure on a non-real-time operating system, but you can it's then executed in the FPGA, so you get some deterministic behavior even in those environments. And we have C, C++, and Python APIs currently, with LabVIEW support separately. We have link analysis applications. So the screenshot in the bottom is showing some SpaceFiber traffic that's been captured across a quad lane link, showing the words and the symbols that are going across that link. And then it's also visualized at higher levels. So this is showing an approximation of the traffic that's been captured on the link, and then you can kind of zoom in and look at the actual detailed traffic. So we also license our IP cores if you want to integrate SpaceWire or SpaceFiber into your FPGAs. So we have interfaces, routers, RMAP initiators, targets, and a processor endpoint, which I'll talk about in a later slide. And our IP is supported in all the major FPGA families from various different vendors, so Microchip, AMD, Lattice. In Europe, we have Nano Explore as well. So the last couple of slides, I want to talk about a couple of things that we've been working on recently, or relatively recently. So a couple of years ago, we implemented remote direct memory access over SpaceFiber. So RDMA is a very CPU efficient method to transfer data across a network from a user space application in one node directly into a user space application in another node. So we built a demonstration running on a Zinc UltraScale Plus using Peta Linux, and the CPU in that device is an ARM Cortex A53. And so the chart on the bottom left here is just showing, similar to the PCI Express device in the previous slide, it's showing data rate and CPU utilization. Now in this case, because of the benefits of using an RDMA style approach, we now get over 20 gigabits per second with less than 1% CPU utilization. And so this was just a raw performance test, but we wanted to build a demonstration that's actually doing something interesting. So the photograph in the right is showing the demo that we built, which is using the DisplayPort interface of the Zinc UltraScale, and it's taking the frame buffers for DisplayPort, and it's actually using them as RDMA memory regions, and we're pulling images over SpaceFiber from the board on the bottom right directly into the frame buffers, and then just synchronizing their output onto the external display. And so this was outputting 60 frames per second using 1440p uncompressed images. And so that's around about 7 gigabits per second data rate. And again, it was well under 1% CPU utilization to run that entire demo. So after we developed this, we wanted to take what we learned from this approach and build a more general purpose interface to our IP. So rather than having to actually use RDMA endpoints on both sides of this transfer, being able to use it in a kind of generic manner, it doesn't require any packet format specifically, and it can be used to communicate with any other device across the network. So one that doesn't even potentially have any software or processor on the other end. So that's what we've been developing recently. So we're calling it the SpaceWire and SpaceFibre processor endpoint. And it uses similar techniques to RDMA over SpaceFiber, so trying to offload as much as reasonably possible to the FPGA and to minimize CPU overhead, providing complete zero copy data transfer from one application through the network to another application. So one of the primary objectives of this was to achieve maximum performance because, as I mentioned in one of the earlier slides, we've now demonstrated SpaceFiber at 100 gigabits per second, and we are aiming for 200 gigabits per second in the near future. So we kind of need a software architecture that will hopefully support those data rates. But the second objective of this work is to have a very simple way to integrate SpaceWire or SpaceFiber into a system on chip. So if you want to add SpaceWire or SpaceFiber into say a PolarFire SOC or a Zinc UltraScale Plus or a Versal SOC, then we've built this IP which works in collaboration with the software stack on Linux, and it's very customizable. So you can be as simple as a single SpaceWire port, or you could have multiple SpaceWire ports, multiple SpaceFiber ports with different numbers of virtual channels and lanes. So it's completely customizable. Although we are primarily targeting system on chips for this architecture, we also want to support standalone FPGAs. So you can host the IP in a standalone FPGA and then connect to that using PCI Express from some other external processor. And because the communication between the processing system and the programmable logic in a SOC is quite similar to communication between a host processor and a PCI Express device, it was relatively straightforward to make the higher levels of the software support both types of device. So just last slide is to point out some of the other standards that SpaceFiber has been included in. So in 2019, SpaceFiber was standardized in ECSS. 2022, it was included in SpaceVPX. It was also included in European Space Agency's ADA specification, and it's been included in SpaceVNX Plus. So this is a small form factor rack standard. So just to summarize, I think the icons here have gone a bit crazy, but yeah, SpaceFiber is TRL 9 since 2021. It's been demonstrated at actually 100 gigabits per second now, with 200 gigabits per second soon, and it's been adopted in various other standards. So we have a demo running outside, so please feel free to stop by and chat about SpaceWire, SpaceFiber. And if there's any questions just now, I'm happy to answer them. So thank you.
Give a hand, please. Thank you. Questions in the house? Don't have any online. Feel free, don't be shy. All right, well, if there's no questions, feel free to ask on Slack or visit the sponsor in their booth. And let's thank David again.
Thank you.